Hello and welcome back for some more deflection using the double integration method. In this lecture, we'll be using Maple as a supporting tool to help us solve the equations and find the constants of integration that'll come out of our solving the deflection. So join me looking at this software package. As we saw in the previous lecture, deflection problems quickly become algebraically very heavy. Even for relatively simple beams, we often have multiple integrations, several constants of integration, and both boundary and compatibility conditions to apply. Maple is useful because it allows us to handle this algebra symbolically and efficiently, so we can focus on understanding the mechanics rather than getting lost in lengthy calculations. It is important, however, to be clear about what Maple does not replace. Maple cannot draw free body diagrams, it cannot calculate reactions, derive bending moment expressions, or decide which boundary or compatibility conditions to apply. All of those steps require engineering judgment, and they must be done by hand. Maple only comes in once those decisions have already been made. Maple fits into the method at a very specific point. Once the reactions are known, the bending moment functions are written correctly, the regions clearly defined, and the boundary and compatibility conditions identified, everything that requires engineering judgment is complete. From that point onward, Maple can take over the mathematics. It integrates the equations, applies the boundary and compatibility conditions that we've specified, and solves the constants, and can also evaluate the slope and deflection. Maple does not decide how the problem is set up. It simply carries out the calculations it is given. So the mechanics define the problem, and Maple solves the equations. So, what is Maple? Maple is a symbolic mathematics tool. It can integrate expressions exactly, solve simultaneous equations, and manipulate algebra symbolically. In this series, we're using Maple purely to handle the mathematics in deflection problems, reduce any errors, and support, not replace, hand calculations. Maple is a general-purpose mathematical software package and has many advanced features. However, we'll only be using a very small subset of the functionality. You don't need to learn Maple programming, and you do not need to explore its wider capabilities for this series. Maple commands are entered into a worksheet. Maple is case sensitive, and the commands are typed after the prompt. The restart command is useful at the beginning of a worksheet to clear previous definitions. A semicolon displays the output, while a colon suppresses it. This can help keep your worksheet tidy. The main thing to be aware of, from my experience with students, is the bit that it is case sensitive. So if you define something as lowercase a, don't then put uppercase A and expect it to work. You have to be pedantic and you have to take your time defining things. To execute a command in Maple, you simply press Enter while the cursor is anywhere on the command line. Maple then evaluates the command and moves on to the next prompt. You can also use the exclamation mark that I've highlighted here, or the 3 exclamation marks to run the whole sheet from the beginning. Before we move further, it's worth briefly clarifying the operators that Maple uses. Some of these may look obvious, but they're not universally familiar, so let's be explicit. For multiplication, Maple uses the asterisk symbol, so A asterisk B means A multiplied by B. Division is written using a forward slash. Powers are written using either the caret or a double asterisk. An equal sign on its own is used for forming equations or logical statements, not for assigning values, which we'll discuss on the next slide. Maple also uses standard relationship operators, such as less than, greater than, and not equal, which you may see when forming conditions or equations. Variables in Maple are assigned values using the colon equal operator. Once a variable is assigned, Maple will use that value consistently throughout the worksheet. Now, you don't need to memorize all the operators we just discussed. The key ones for this series are multiplication, division, powers, and the distinction between equal and assign. Once you're comfortable with these, following the Maple examples becomes much more straightforward. We will mainly use symbolic variables, but numerical evaluation can be done later if required. Maple is capable of many advanced mathematical operations. For our purposes, however, we will deliberately restrict ourselves to only the functions required to solve deflection problems using the double integration method. This will keep our focus on structural mechanics rather than the software. So, as I mentioned, for solving deflection problems, we only need a small number of Maple commands. These include defining equations, integrating using int, substituting values with subs, and solving simultaneous equations using the solve function. These are the commands that we'll need to follow the examples in this series. In this next section, we'll apply the process to a worked example. We'll start from a beam with a known bending moment, state the boundary and compatibility conditions, and then use Maple to integrate the equations and solve for the constants. And finally, we'll be able to extract the slope and deflection expressions. And finally, to the worked example. We solved this worked example in the previous lecture by hand. But just a reminder, we've got a simply supported beam with a uniform cross-section. It carries a point load. Our objectives, once again, are to determine the equation of the elastic curve, the slope at B, and the deflection at B. As we've already solved this by hand, our aim in this part is just to show how Maple can support the solution once we know the bending moment. So, just a reminder of the procedure before we begin. We need to do all the things that require engineering judgment, which is sketch the elastic curve, figure out what the bending moments are, and if there are discontinuities, write them for each region. We also need to figure out the boundary conditions and the compatibility conditions. It's essential that all of these are correct. Maple is a mathematical tool. It doesn't know whether the conditions we've given it are physically correct. It'll just solve whatever we ask it to solve. And once we've done everything that requires engineering judgment, from this point forward, Maple will just be used to carry out the mathematics, integrating the bending moment expressions, applying the boundary and compatibility conditions that we've given, solving the constants, and evaluating slope and deflection. The quality of the Maple solution, therefore, depends entirely on the quality of the setup. Here we're just going to give ourselves a reminder of all the parts that we've already solved by hand. First, we sketch the expected elastic curve based on the support conditions and the applied point load. The beam is simply supported, so the deflection is 0 at both supports, and the deflected shape is smooth and continuous. Because the load is discontinuous, however, the bending moment changes form at the point load, and the beam is divided into two regions. At this stage, we also define the coordinate system carefully. In each region, coordinate x is measured in a consistent direction along the beam, and we must be clear about where x is defined in each region. These choices matter because the bending moment expressions and later the deflection equations depend directly on how x is defined. As we did previously in this example, x1 goes from A to B and x2 goes from C to B. On this slide, the support reactions have already been found and are shown on the diagram. We now divide the beam into the two regions we discussed based on the location of the point load. Region 1 runs from A to C, and the local coordinate x1 is measured from A towards the right and is defined between 0 and A. The bending moment, therefore, as we defined in the previous session, is PB over L times x1. Region 2 runs from C to B, but here the local coordinate system x2 is measured from the right hand back to the left. x2 is defined between 0 and B. With this coordinate choice, the bending moment in region 2 is PA over L times x2. It is very important to notice that the coordinate directions are different in each region. These choices are deliberate, and we discussed them in the previous session, but we must be careful to use them consistently when we integrate the bending moment later. Maple, as we've already said, will not question the definitions. It'll just work with whatever expressions and coordinates we give it. And finally, a reminder of the boundary conditions and compatibility. Because the beam is simply supported, the vertical displacement is 0 at both supports. Using the local coordinate system shown, it gives us that y1 when x1 equals 0, and y2 when x2 equals 0 equals 0. And finally, we remind ourselves of the continuity or compatibility conditions at point B. From the physical behavior of the beam, we know that both the displacement and the slope must be continuous at this point. The beam doesn't break or hinge at B. The deflection condition is straightforward. The vertical displacement in region 1 at x1 equals A must equal the displacement in region 2 at x2 equals B. The slope condition requires a little more care. Because the coordinate x2 is measured in the opposite direction, the slope changes sign. This is why the continuity condition is written with a minus sign. Taken together with the two boundary conditions, we have 4 independent conditions for 4 unknown constants that will develop when we do the double integration. These are the exact conditions that will be given to Maple, so it's essential that they're written correctly. And now we move on to Maple. At the top of this slide, I've included a small graphic of the beam. This is just being copied as a visual reminder of what we're solving. It's not essential for Maple, but it helps us keep track of the regions and coordinates as we work. The first Maple command we'll use is restart. It clears any previous definitions and ensures that we're starting from a clean worksheet. We then assign the bending moment expressions for each region. The key thing to notice here is the colon equal symbol. In Maple, this assigns an expression to the variable. It tells Maple that this is the definition of the bending moment. So for region 1, we assign PB over L times x1, and for region 2, we assign PA over L times x2. Exactly the same bending moment expressions we derived by hand. Maple is now storing them so they can be used in later steps. Now, if you end the command with a semicolon like I have, in blue will appear the command you've just executed. If you put a colon on, it'll still assign M1, but it won't recall it on screen. On this slide, we use Maple to perform the integrations required by the double integration method. The Maple command int means integrate. The first argument is the expression being integrated, and the second argument is the variable for integration. So for region 1, we integrate the bending moment expression M1 with respect to the local coordinate x1. And using Maple notation, this is written as int m1, x1. We then assign the result to the slope expression, including a constant of integration. We do the same for region 2, integrating m2 with respect to x2, and introduce a constant of integration. We then move on to integrating the slope expressions once more to obtain the deflection in each region. Each second integration introduces an additional constant of integration. At this stage, Maple has generated general expressions for slope and deflection in both regions, but the constants are still unknown. These will be determined next using the boundary and compatibility conditions. On this slide, we apply the boundary conditions in Maple. The Maple command subs means substitute. It replaces a variable with a specified value inside an expression. In the first line, we substitute x1 equals 0 into the deflection expression for region 1 and set the result equal to 0. This enforces the boundary condition that the deflection at the left support is 0. In the second line, we substitute x2 equals 0 into the deflection expression for region 2 and again set the result equal to 0, enforcing 0 deflection at the right support. As you can see, Maple simplifies these conditions automatically, and in this case it immediately shows that C2 and C4 must be 0. These are 2 of the 4 constants of integration. The remaining constants will be determined using the compatibility conditions next. On this slide, we apply the compatibility condition for slope at point B. I've done this in parts to make it easier to follow. So we start by evaluating the slope expression in region 1 when x1 equals a. This is done using the subs command, which substitutes x1 equals a into the slope expression and stores the result as equation 3a, or EQ3a. We then evaluate the slope expression in region 2 when x2 equals b, again using subs, and store this as equation 3b, or EQ3b. Because the beam is continuous, the slope must be the same at point B, and setting up equation 3a to equation 3b with the minus sign gives us the slope compatibility equation, which I've stored as equation 3, or EQ3. We now apply the compatibility condition for deflection at point B. As before, we substitute x1 equals a into the deflection expression for region 1, giving us equation 4a. We then substitute x2 equals b into the deflection expression for region 2, giving us equation 4b. Because the beam remains continuous, the vertical displacement at B must be the same when approached from either side, so setting equation 4a equal to 4b gives the deflection compatibility equation. Together with the 2 boundary condition equations applied earlier and the slope compatibility, we now have 4 equations for 4 unknown constants, and the system is ready to be solved in Maple. And finally, on this slide, we can ask Maple to solve the system of equations we have constructed. The solve command is used to solve the 4 equations. As you can see here, the way it's written is solve, open brackets, then in curly brackets, you write out the equations that you want to solve, comma, and then open another curly brackets and write the variables for which you want to solve the equations. This solve is wrapped in the simplify command so that we get constants in a clean simplified form. The results are shown on the right-hand side. At this point, Maple has determined all four constants of integration. Notice that this includes the values we already identified earlier, such as C2 and C4 equaling 0. We then use the assign command to substitute these constants into the slope and deflection expressions automatically. This means we no longer need to carry the constants explicitly. They'll now be built into the equations. And finally, we define the deflection expressions in each region, this time dividing by EI to obtain the physical deflection. These simplified expressions labelled y1 and y2 are the final equations of the elastic curve for regions 1 and 2 respectively. At this stage, we have complete analytical expressions for deflection across the entire beam, ready to be evaluated at any point of interest. As a final step, we can evaluate the deflection at point B. Using the Maple command subs, we can substitute x1 equals a into the deflection expression for region 1. This will give us the deflection at point B, which we can label as y max, since we know that this is the maximum deflection. The result is shown on the right hand of the slide. We could have also done this by substituting x2 equals b into the deflection for region 2. We can compare this directly with the result from the hand calculations that we derived in the previous lecture. And as expected, the two are identical. We can do exactly the same thing for slope, so derive the full equations and then substitute any value to find the slope at any point along the beam. This confirms that the Maple solution is consistent with our hand calculations and that the mechanics, boundary conditions, and compatibility conditions were all set up correctly. Maple has simply provided a clean and efficient way to arrive at the same result as the hand solution. Now, in this example, the problem was not too difficult to solve by hand. However, you can already see how for a beam with more regions and therefore more constants of integration and more simultaneous equations, the algebra would quickly become lengthy. In those cases, Maple becomes particularly advantageous, not because it replaces the mechanics, but because it handles the mathematics efficiently and reliably once we've set up the problem correctly. I hope that was helpful and that it provided you with the tools that you needed to go and solve some more complicated deflection problems.